My name is Yuval. I lead sales and marketing at QuEra, and we're all here to make an impact, right, with Q. I joined QuEra full-time not too long ago, and I was determined to make an impact with a Q. So I went to the website and changed all the C's and K's to a Q. So it was computer, consulting, credits, and so on. People were a little bit worried about that, but then I realized, or they realized that it was April Fool's, April 1st, so I got away with it. But they did tell me to focus on more serious things. So what I'd like to tell you a little bit is what we can do with our current computer and where we're going. I want to give you a taste of the future there. The dual mode quantum computer. And so just a little bit about QuEra. So we build quantum computers based on neutral atoms. Our 256 qubit machine is available publicly on Amazon Braket since November last year. This is so important, I'm going to say it again. Our 256 qubit machine is available publicly for the last 6 months, meeting the Amazon SLAs. We think it's the largest publicly available machine in the world. And although I can't disclose the exact statistics, we see dozens of organizations that use it consistently, both on Amazon as well as directly with us. So it's not just a toy or a research gimmick. People are doing actual work with it. And our strategy all along has been to deliver, although we continue to march towards a fault-tolerant, large-scale quantum computer, and we think we have a very clear path to doing that. We've always been focused on how can we deliver value at every stage. Part of that, of course, if we had $500 million, we could say, hey, come back in 5 years and we'll give you everything you want. But since we don't have $500 million, we've decided sort of to take the step-by-step approach. So what's unique about the machine? So it does work today in analog mode. I'll talk about that in a little bit. 256 qubits, fully coherent system. And it's built to be dual mode, meaning it's built to be both analog mode, which we'll talk about in a second, but also support universal gate-based mode later. Part of the power of quantum computers and part of the power of neutral atom quantum computers is that you can map the problem not just into gates, but also on the physical arrangement of the qubits, like those that came before me, like Adam and Pascal. Our individual qubits are individual atoms, in our case rubidium-87, and we can arrange them in space. We call that a field programmable qubit array. So a little bit of a take on the FPGA, the field programmable gate array that revolutionized electronic design. We can encode a lot of the constraints and simplify a problem by encoding it into the physical position of the qubits. So just to talk about analog versus digital, as you know, a problem could be universally decomposed into single and 2 qubit gates, as you see on the left. Whereas in analog mode essentially lives up to Feynman's vision. If you read Feynman's presentation at NASA in 1982, he said, well, you put these atoms and then the Hamiltonian goes into play and so on. So a lot of problems could be expressed as Hamiltonians, as the interaction between the atoms. We can set up the atoms in a particular way to match the problem, and then we let the system evolve and measure it. So what you see here, for instance, this is a real image, 256 qubits, 256 atoms. You could try it out this afternoon on Braket. And of course, we can arrange them any way we want. We can arrange them this way, and we can arrange them to look like the map of the world. And we can even, move them around over time. So this is sort of the hello world on the QuEra system by taking consecutive pictures of the atoms. Well, what is it used for? What can people do with the existing system? So we see 3 key applications: machine learning, optimization, and simulation. And you could say that's not surprising. You've heard machine learning, optimization, and simulation before, but let's dive a little bit deeper into each of them and see an example. So starting with machine learning, one of the things that we know prior to quantum computing is that people try to do classical neural networks. In a neural network, you have a set of input nodes, you have one or more layers of hidden nodes, and then you have output nodes. And then, as we've seen today with GPT-4 and others, you have billions and billions of parameters, and training the network to learn what you want to do is very difficult. Adopting this approach to quantum computing is nearly impossible today. First, we don't have billions of parameters. But then a lot of the training classically is about estimating the gradients and adjusting the parameters accordingly, and with a noisy system that just doesn't converge. So an approach that has been promoted earlier in classical computing is called reservoir computing. And in reservoir computing, you have the same input. You have a reservoir that could be anything from a bucket of water or something else. And you measure outputs, and then the training is really about, so the reservoir has sort of interconnected components, and what you do to train the system is basically linear optimization, linear regression on the output. So there's no super complex adjustment of the parameters in the reservoir in the middle layer, so no quantum training is required. And reservoir computing already is successful in analyzing and both in classification and prediction of very complex systems, so weather systems and so on. So we said, well, what would happen if we take the same approach to quantum computing? So the concept is basically this. We take input data. Here it's an image, but it could be something else. We downsample it, so you could do principal component analysis or any downsampling that you wish. You then feed it into the reservoir, in our case, 256 qubits. You let the system evolve just on its own, and then you optimize, you do classical linear regression on the output, and magically, at least for the slides, right, the horse image gets classified as a horse. And the advantages is that this is feasible. It works on today's machines. It's trainable. You don't have vanishing gradients or other issues that are common with classical training. And it's very fast. And so just to demonstrate this, I think that's sort of the classical example, handwriting recognition. So we took a lot of 10,000 training samples. We did a principal component analysis. We fed them into the reservoir. And what you see here, you see 5 bars. The 2 left one and the 1 right one are sort of classical methods. But I want you to focus on the third, the orange one, and the one next to it. Here's what's happening. When we allow the qubits, the atoms, to interact with each other, to entangle with each other, we get the orange bar, which is on par with classical methods. When we take the atoms far apart and we don't allow them to entangle with each other, then the performance is awful. In a good way, I could say, looking at the glass half full, I could say that allowing the system to bring out the quantumness allows us to improve performance very, very significantly. And why is the QuEra system interesting even in its current state for machine learning? Because with 256 qubits, you can encode a very large input space. So you can encode very many parameters on the input. And 2, because we leverage the quantumness of the system, you can get these hidden relationships between the inputs and get some very nice results. Obviously, this is just a simplistic example. We've done it now for others. Happy to talk about your ideas or your challenges as well. Second topic is optimization. And this is, again, a situation where we can leverage the geometry of the system to encode problems in a simpler way. I apologize for the font that looks like it's gotten too large here, but one of the classic optimization problems is called maximum independent set. And a maximum independent set has a graph, and your goal, and the graph has vertices that are connected by edges, and your goal is to find a solution that no 2 connected vertices are of the same color. This could be a cell tower problem. I want to put as many cell towers as I can without them interfering with each other. This could be a Starbucks problem. I want to put many Starbucks in a given city, but I don't want them too close because I'm just sort of wasting resources. So how do you do that on a quantum system? So we have an example. This is something that's on our website in a published application note. So the goal here was to take a map of Manhattan and Starbucks. We originally started with a map of Boston, where QuEra is, and talk about Dunkin' Donuts, but decided at the end to go for Starbucks. Good for these kind of conferences, right? Better than donuts. So the purple dots are potential locations for these Starbucks. And again, we want to make sure that no two Starbucks that connected are actually chosen. This is what it looks inside our system. So we basically taken that map and encoded it in the positions of the neutral atoms. So you can see that sort of matching between the map and the position. Now, the way neutral atoms work in what's called Rydberg blockade is that once you let the system evolve, if atoms are sufficiently close, they don't allow two atoms at the same time to be sort of at the one state. So we basically just encoded here, let the system evolve, and then we basically got the solution. So unlike a gate-based system where we would have to encode the constraints programmatically, here we encoded the constraints geometrically, and that allows us to solve much larger problems with a given quantum computer. And our experts, scientists, and engineers have shown, both published and shown to customers, that it's much beyond max-independent set, that there are many problems that you could encode in such a way that using an analog quantum computer gives you substantial advantages. And the third area is simulation. We've published extensively in Science, in Nature, and so on. This is just an example of exotic phases of matter, discoveries that were predicted but couldn't be measured. And now physicists that want to simulate systems where quantum effects play a big part in their evolution can encode them and then run them on our system. So let us peek into the future. So we talked about simulation, we talked about optimization, we spoke about machine learning, but where's this going? Well, one direction that it's going is massive scalability. So this picture, borrowed from the University of Chicago, shows a grid with 10,000 points. As you remember from the previous speaker and others, in neutral atom machines, every atom is trapped by a beam of light. So here's a picture showing 10,000 beams of light. So we can go to at least 10,000 qubits without needing interconnects. This is a big deal, right? Because in other technologies, very quickly, whether you use superconducting or elsewhere, at some point you start needing interconnect between modules, and here we have 10,000 atoms, or would have 10,000 atoms, trapped at 4 microns apart, so this is tiny, 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 and single module. The second thing, so this is a video from published research from our collaborators at Harvard. And what you see here is essentially what we call qubit shuttling. So these dots are the atoms, and they can move around. And the amazing thing is that they can move around while preserving their quantum state. So you could get an atom over here, and then entangle it, and then move it elsewhere, and move it elsewhere, and continue to do this. And that allows you to do some truly amazing things. First, it allows us to do what we call multiple zones. So you could say, I have this big grid, and I'm dividing it, at least logically, into 3 areas: a compute area, a memory area, and a mid-circuit measurement area. What I mean by that is you could have qubits on the side, let's call it the memory area, in a state that has very long coherence time, so they're just there. And then when you need to do a computation on them, whether on physical qubits or logical qubits, you bring them into the compute area, and then you do whatever you need, and then you can take them elsewhere. You can also create that third stage, that third area, And imagine that today, to measure a quantum system, to measure a neutral atom system, you basically take a photograph. Imagine if I had an area that's separated, where if you took a photograph, it only photographs and measures only that portion and not others. So now you could do mid-circuit measurements, which is the key for error correction and many other things, just because you can do this qubit shuttling. The other thing related to that is that in neutral atom, and especially the way we work here, there's no need for a control line for each qubit. And let me explain what that means. When you look at a superconducting system, for instance, every qubit needs to have several control signals that go to it. But that's not really scalable. I mean, imagine opening your 4K television and discovering that each pixel needs a wire. That would not work. So in LCDs, there is a system that requires much, much fewer control signals, but can still drive all the pixels. This is what we're doing here. And this is one other reason that we're so optimistic about scaling. So I've shown you 10,000 spots of light. I've shown you qubit shuttling. And because of that, we don't need 10,000 control signals for 10,000 qubits. And that shuttling also gives you that, what we call all-to-all connectivity. So you're not limited by the physical, oh, this qubit has to be next to that qubit, and therefore if I need to entangle them, I just need to sort of do it sequentially. So this gives you lots and lots of flexibility on the way to full-scale, fault-tolerant computing. And it does give you also error correction. So the fact that we can move qubits around both allows us to test error correction codes. We don't have to stamp out a chip every time we make a change. We just configure the software, and the qubits are configured differently, are placed differently. We can do simultaneous operations on multiple qubits, which lends well to doing arithmetic on logical qubits, not just physical ones. And this Nature publication from our Harvard collaborators showed, toric error correction code on a torus, which is, so scaling, control, different zones, and now error corrections. These are all things that, we see in our not too far future. In terms of quantum roadmap, real quick, so we have a system today. You can use it this afternoon. We're going to both enhance the control of the system, so you can do finer control, expand the number of qubits. We're adding digital gate-based mode, so you'll have a system that does both, that does analog and digital. And I specifically meant to say analog and digital, and not analog or digital. And the reason is that some actions are better done in an analog way. So for instance, state preparation is easier and faster to do in an analog way. So imagine preparing a state in an analog way and then processing in digital mode. So you can do a lot of really cool things when you have this dual mode machine. And then scale it to get to fault tolerance, larger and larger systems. How do you work with us? 3 ways. One, we're happy to work with you on individual projects to see if your challenge is applicable to our machine, help you benchmark relative to other quantum computers or to quantum-inspired algorithms or to classical solutions. We also offer premium access, which means, yes, you can access the system on Amazon, but you can also access the system directly from us and get support from our engineers and get additional benefits. And we're also happy to discuss machine sales or leases, basically, for those that want a quantum computer of these capabilities on site. We're happy to do that as well. So just talk to me, and happy to talk to you about questions or anything else. Who's got the first question? I can't see anything, but I trust you guys can.
Yeah, just a quick question. Do you have any estimates on the timeline for introducing dual mode?
Not too far. Let me put it this way.
Other questions?
And the thing I told you about changing the K's and C's on the website to Q's, don't try that at home.
Hello, thank you for the talk. The demonstrations from the papers were super interesting. Do you also share some complexity analysis or correctness or convergence analysis? Like, can we expect physical simulations like you've demonstrated with the map to converge and converge faster like we do on classical resources?
So we have some papers that discussed sort of benchmarking. So for instance, we are showing that for certain optimization algorithms, neutral atom machines scale up faster than quantum annealers, for instance. But we can talk about, if you have a specific question, I'm happy to answer it offline or connect you to one of our scientists. Any other questions?
For their machine. All the examples you showed were 2D. Do you have a plan to move to 3D, or are you just going to make the grid even bigger?
I think we could move to 3D, but at the moment we don't think it's necessary. I mean, let's get to 10,000 qubits, and then we'll see if we expand it even more, or do we need to add another dimension.